Okay, hello everyone. Welcome to the Abacus tutorial workshop 2. And in this tutorial, we are going to simulate a fire test of a restrained column exposed to the fire. And in this workshop, we are going to perform the structural response analysis using beam element and using cell element. So we have this problem definitions. So here we have a colon, resistant colon. So the colon is made of the uh, uh, this I-beam, which is the test specimen in the middle, and this I-beam in the middle, which is the test specimen, and then it is supported by two steel plate on the top, and then there is this support, the boundary condition or the support applied in the end of the two plate. So this is the fire test conducted by Ollie and Corner. So you can find the detailed information of this fire test in these literatures. So Ollie and Corner tested both axially and rotationally restrained column under fire, and the steel column is made of 127 by 76 UV 13 I profile. The length of the column is 1800 meter. Both end of the column were welded with uh, two this 200 by 750 into 40 millimeter steel plates. So these are the uh, bottom and the upper steel plate, and these two plate provide rotational restraint in both end of the column. So these are welded and they provide the rotational restraint, and the end of the top and bottom plate were connected to the rig using two light bulbs in each. So the edge restraint can be considered as simply supported, and the imposed stiffness of axial restraint is around 57 kilonewton per millimeter, and on the top of the column the axial load of 205 kilonewton is applied. So in this point column, or maybe here, the load is applied. So the column of the length around 750 millimeters. So this length, which is shown here in the red, so this is heated, and um, both top and bottom plate are located outside the furnace, which means that these plates are not heated, and the column temperature in the different location are measured using thermocouples. The average column temperature shown in this figure, in this figure in the figure in this figure uh, in this figure below is shown, and the average column temperature curve will be used in the structural analysis. So this is the heating due to the fire in this case, and the detail on the test can be seen in Ori and Coron in this reference literature and also in the project documents. Okay, so our task in this model is to create a simulation model using beam element and cell element, and the beam element we create use in the beam element. So the AB is the lower plate and CD is the upper plate, and there is an axial resistance where we need to create the spring axial resistance. There we create the spring, and then we apply the boundary conditions at the end of the this upper and lower plate, and also some boundary condition in the connection between the column and the plate. So first task is to create a beam model as shown in this figure, and the second task is to create the same model using a cell model. So here is the similar model and using beam and the cell element. Okay, and now the structural analysis procedure in Abacus for this type of example is if we are going to add the geometric imperfection in the model, then we have to perform using this approach. So first we create the model as we are going to create the model for the structural analysis, and then we separately perform the linear buckling analysis, and then we write this this node field command at the end of the output request, and then we obtain the desired mode shapes, the buckling shapes for the dynamic analysis, and then we link the imperfection with the result obtained from the buckling analysis. So we will link the result obtained and then finally run the dynamic analysis procedure. So this is now we are in the part module, and in the part module this is the restrained column exposed to the fire simulations using beam using cell element. And now in the previous tutorial we have done the same example with the beam element, but now we will do the same example using a cell element. And here are some little extra things that we will model these extra points where we model to this provide this MPC constraint. So we provide the boundary condition in this point and distribute that over the over the connection connection of the in colon in and the plate. So we have these two extra this type of point where we apply the boundary conditions and then apply distribute the properties boundary condition property to the in colon connections. Okay, and now here the colon and the two in plate were modeled as a surface geometry following the dimension from the fire test. The thickness for the flange and wave for the colon were assigned in cell thickness definitions, and similarly the thickness of two in plate was also assigned using the same approach. Now the rest in colon structural model using cell element is shown here in this figure, and our target is to model the structure in this way. So now this model we will follow the approach that will model a part in the part and in the part in the part and in the part model we will model this structure as a different part, and then in the assembly model we will make the assembly of the this structure which looks like this. So first we will make a model part model for the column using a cell structures, the surface geometry, and then we will also model the second part as the upper plate, third part, and then similarly we have this discrete point, and we will also model them as different part. The idea here is that we will it will be easy for the assembly, and then the idea is to start our reference global 00 point in the bottom point in the middle of the cross section of the column lower end where the plate is connected, and below that one we will create uh, another discrete point there 50 mm below there, and similarly we will create 50 mm above the top in of the column, and then we'll assign a spring in these 2 points. Okay, so that's the idea for the modeling the part. Altogether we will make 6 parts in the part model, and here a spring is used to model the axial restraint of the column in point F. So in this point F, so this is the point F here. So a spring here between this point, so a spring is used to model the axial restraint of the column due to the vertical support system as shown in the figure below, and a discrete point in the position 100 mm above the column in plate connection is created. So the length of this 2 point is 100 mm, and to model axial resistance and a spring element is assigned where the discrete point and the colon in plate connection nodes. So this is another discrete point. So, and here the idea for the this applying boundary condition is that we will apply a boundary condition in these two discrete point. So in this point we will apply the boundary conditions, and that will be distributed over the this these connections of the uh, connection of the I-beam profile in the cross sections connections there, and it will be distributed using this multiple point constraint using beam type of constraint. And then similarly here, and this is the point where the force, this is the point where the force is applied. So the force is applied in that point. So we model now the geometry in the part model, and then we try to keep our 0 0 position for this one. So we will model using the exact dimension for this reference discrete point reference point, which will be easily available in the assembly models once we go that one. Okay, so now let's go to the part model first and then create those 6 parts. So we are now in the Abacus windows. So we go to the part model. So we need to select the part model, and then we need to create a new part. And the part is now, we name this as the colon part. So colon part, and the modeling space is 3D type deformable, and the base feature is cell, and then we create a cell section, and then we extrude that one, so which means that our type is the extrusion. And the approximate size for the grid for the sketching is that it's always good to have the double of the cross section length. So now we are going to create the I-beam 120 by 76. So it's better to have around 350 the grid of the cross section grid for the sketch. So now we are in the sketch mode, and then now we need to sketch the section for the cell extrusion. And then now we start creating with these create lines options below the module. So here is a create line options, and then now we will start this one in 0 0. So let's start in 0 0, and then the the width of the I-beam is 76, so 76 0, and we accept that one, click the middle button, and then we will also go in the midpoint of that one. And similarly, which is the 38, so 38, and then the height of the I-beam is 120, so 38 120, and then accept with the middle button. And similarly, we need to create another point from 0 120, and then we need to go to 30 76 now, 76, and then that is 100 120. So we have the section created. Now then we can now accept that one with the middle mouse button, and then it will ask us to sketch the section for cell extrusion. Yes, it is done. And then the height, which is our extrusion length, now it is 1800. So we click as 1800 and then accept that one. Now our beam, our column is created. Okay, so in the part we can see that our column is created with the sketch of the cell, and then it has been extruded. So we can edit our definitions from here. So if we like to edit our sketch, then we can see here, and also we can have the dimension here. So it is 76, and then also the dimension for this dimension for the height of the column. So if we like to change that the dimension, then that is also possible. So we accept that one, and also here we can change we can change the depth of the extrusions. Okay, so now we have created the column part, and similarly now we will create the another part, and another part is the upper plate, upper plate, and then it is the same 3D deformable, and the base feature is the cell, and then we will use the extrusion. And now here we will use the 1500 as the approximate size, because I'm going to sketch the 750 uh, for the lower plate. So now let's create that one, and then we start with 00, so 00, and then 750 50 0, so we have this one, and to be confirmed we can check the dimension. Okay, it's 750. Then now we will accept that one with the middle mouse button, and then sketch the section for the cell extrusion. Yes, done. And now we do the extrusion up to 200, and then our uh, upper plate is created. And now we will use this this partition of the face in order to make the assembly procedure easy in the assembly model. So we will now try to make uh, our partition in this way that it is easy to apply the connection between the I-beam, I-profile cross sections and this point. So we will now have this type of partitions, which is shown over here. So we will use that kind of partitions. So the idea is to have this partition from the middle one time, and in both directions, x and y, and then some extra partitions so that the I-beam cross section will match directly to the plate. So that's why we need to do the partitions. So let's go to the abacus, and it will be easy for us in the assembly procedures. So now let's create partitions. Yes, create a partitions, and then create the partition of the face, and then we need to select this face, and the face is selected, and then select using sketch. So, and then we need to give one edge, select an edge or axis that appear vertical and on the right. So we can select this one, so it will come in this way. And now we need to create the sketch for the partition of the face. So we will create one in the middle in vertical direction, and similarly another in the horizontal direction. So, and now we need to also create these other two lines, so we will create that line also. Yes, that's horizontal, other one line, another horizontal line, and uh, and we accept that one, another vertical line, and also another vertical line. So we need to now modify the dimension for this one. So the dimension for this two is 60, so 60 this one, and similarly the dimension for this one is also 60, and this is also 60, and then now the dimension for this is 38 from in the horizontal direction. So this is 38, and also now this is 38. So now this is now okay. So this length we can see that that's the I-beam definition, 76 by 120. So that's why we have the 60 and 38 uh, for the partition of the face. So now our sketch is complete, and then we can accept that one. So our now done. So we have the part ready, the upper plate. And what we can do now, it's the same. So we can copy this and name that as a lower plate. We can name this as a lower plate. So lower plate, and okay. So we have now three-part column upper plate, lower plate, and upper plate. Okay, now we need to create those discrete points. So now we need to create those discrete point, and this is one is minus 50 mm below the 0, 0 point, and another is above 50 of from the in of the colon top, and then 100 mm above the for the in point of the spring. So we need to create these three parts. So now let's go there and create them as a single part, so they will appear in the assembly. So let's say now we have this, let's name this as a name as a discrete uh, sorry, let's name as a discrete point. So discrete point and discrete point, that is uh, low below the lower colon. So lower colon discrete point below lower colon. So we can say below lower colon. So discrete point below lower colon, and now we need to change the type as the this as a discrete rigid, and then now the base feature is a point, and then we need to give the coordinate of that one. So the first coordinate is in y direction, minus 50. So and then accept that one. So our discrete point below lower colon is created, and here we can see that there is a reference point created, and we can edit the dimension of the uh, dimension, which is below minus 50, then apply. Okay, so what we can do is now we can copy this one and then change that discrete point. This is above the which is above the upper colon, but that is the loading point we can name. So we load in that point. Okay, and we have created in the loading point, and now we need to change the position of that one, and the position is nothing but this is 1800 plus 50. So this is 1850 because the height of the colon was 1850. Then we apply, and so now we can see here it is 1850, and we can bring that point with this auto fit view. Okay, then again we need to create one more copy of this one, and that is the discrete point at in spring. So end of the spring. So we have that point, and then also we need to change the coordinate of the point, and that is now plus 100. So which is 1950. Then okay, and then yeah, so we have created, so there are altogether 6 part, and the way why we create this type of approach is that it will be easy to modify and also in the assembly models. Okay, so what we can do now is that we can go in the assembly model before going to the property model. It's all right. Let's see how our assembly will look like, and we will assemble that one and then come back to the property model. So let's go to directly in the assembly model, although our second step is the uh, property model, because the idea here is to see how this part will appear in the assembly model. So now we have this colon, yes, and then we have this discrete point, yes, this discrete point, and the lower plate and also the upper plate. So they appear in this way, and then we choose this independent mesh on instance, so we can directly mesh selecting on the all parts rather than meshing each part individually. Then we accept that one. So we have bring them here, and this discrete point, they are the same the way how it should be, because we have used the coordinate definition in the while making creating the part. but now we have to translate and rotate these column and the plates, so to make the actual assembly, and we can do that one in the assembly model. And here in the assembly model we will uh, we will do that. So let's see the let's see here. So our next step is to create the property. I have jumped this one, and now I have in here in the assembly model, and in the assembly model we will create instance. So we have create the instance 6 instance from 6 part, and then we will create the final assembly of the parts, which should look like this type of structures. And then we will also add the spring, the engineering features like spring or dashboard or fastener in this model. But now in our model we will only have this, only have this spring, so we will add a spring between those two in the assembly models. So first let me make the assembly of this part, and then we will go back to the property model and then come again back and then assign the spring in the assembly model. Okay, so to the abacus, and then now let's organize this assembly. And now we need to first we in order to have that kind of orientation, so we need to rotate and translate this part. So now so we have this x y z, this type of coordinates, and our beam should have this y direction, which is the height directions of the column. So that can be obtained by rotation x. So now let's rotate the instance. So now it will ask us to select the instance to rotate. So now we select this column, then accept, done, and then now select an axis or start point for the rotation vector or enter xyz coordinate. So but now I will select an axis, so we go in this axis, and here we select the x-axis, and when we go close to x, the color will change. So now you can, I go away and I again go back, the color will change. So in this way you can select the axis and then select, and then there will be a arrow in the x, and then we have to give the angle of rotation. So now in this case it is 90, and we can leave it default, and then we click the middle button, and then it will show you a preview. Yes, it has been rotated the way we liked, and then we have to okay the partition, uh, the position of the instance. Okay, and it has been okay, but now we like to make this point at 0 0. So we need to translate the instance. So click on the translate the instance, and we need to select the instance to translate, and then done. And then now we need to click on this the the below position. Yes, this is the position, and then we would like to move this one to 0, so we can select as default, and then we can have auto fit there. And now our we have this y direction in the height of the column, and there is this 2 point above the top in of the colon, and below the colon there is this another point. So this is the exact way how we would like to have the definition. So let's accept the position of the instance. So this is done, and now we need to also move these two parts to the upper and the lower part, so we can translate them. So let's first select the instance, and then we need to go and choose this the middle of the plate, and then the middle of the plate should go for the first one in the middle of the top, and it is, so we can click that one, it goes away, and then we need to accept the position of steps instance. So it looks the way how we like. And now now also we need to move this instance, and then similar process. So we have this point 0 0, and then we go to this 0 0, then accept the position of instance with OK. And now let's cancel the procedure and then go to auto fit and have this orientation. So now it is, now we can rotate and see if everything is okay. So yes, it is now exactly the way how we like to have the uh, connection. So this eye cross section, this eye cross section is exactly matched with this plate. So let's have a default view, this default XYZ view, and then now we need to go back to the property because we have not assigned any property here. And then let's go in the column model, and then we can assign the property. But now let's bring the material data and also the temperature of the average temperature, measure average temperature to this one. So to this one we can use this ready-made Python code which is available in the description below in the input files. So so on the input file there is this restrained colon mat temperature Python code. So if you run this one, then the material that is needed for this, an example of the material for the still linear and non-linear, as well as the amplitude of the fire temperatures in the test can be obtained. So we run that one, and then we have this still material linear and non-linear, and then also the column temperature. So we can have a look in this still. So this still linear is the linear material with density and the elastic property, Young's modulus and Poisson ratio. So we use this elastic material to model the in plate of the two plate, and now we have this still non-linear which has the density and temperature dependent elasticity, expansion and plastic. So we will use this one, the temperature dependent data of this one still examples, and then we will use this one for the column, because only the column is heated. Okay, so we have finished importing that one, and now we need to create a section. So let's start creating a sections. So in now we need to have here three sections, and then we need to have these three sections there, and then we need to assign the section for each individual parts. So let's have the first section as a section flange. So we can name it as a section flange. So section flange is a category is the cell, and we choose the homogeneous type, and then continue, and then this window appear, and then we can see the name of the section is the section flange, and type is a cell continuum or cell homogeneous. So and then we give the thickness of the thickness of the thickness of the flange, that is for 7.6. And now here we need to assign the material, and now here the material is still non-linear because we assigned for this one for the I-beam. So and then we can accept that one. And now similarly we can create we can go to the manager here, and then we have create this section flange. So we can similarly go there and then create section wave, and then it is same cell homogeneous, and now here the wave thickness is 4.2. So 4.2, and also we need to select the material non-linear here, and then we need to accept. So we have created these two sections, and for the flange and wave. So the I-beam section definition is complete. So we need to create this another section, and that is for the plate. So let's create the section plate and name it as a section plate, and it's the same homogeneous cell category structures. And then we continue, and the value now the thickness of the plate is 20, and now here we change to still linear material, not the still non-linear. Okay, so still non-linear, still linear. So in this example, we can see that we can use different material model for different part of the structure. So we simplify the place which is not having the heat affected. We don't need to give the temperature dependent, and we assume that the part can be a linear elastic part. Okay, so we have three sections complete, and now we need to assign them to the geometry. So we go to this section assignment, and then now we need to select the part. So now here, let's say this is wave part, and then we are in the column part, and then this is the wave we can select. Okay, we select and create the set, and now here we see that for the wave region we need to give the section wave, and we can leave this definition and mid surface for these examples. Okay, so that is created for the web, and then we can look from the view part display option, and then we can render the cell thickness and apply, and see here that in this, okay, the definition is uh, completed. So let's remove that one, then apply. Okay, similarly we can do for the upper flange. We can do the upper flange here, so we can select this, and another flange that one, another flange that one, and then done. And now this is the section flange, and then we can leave other everything default for this example, cell offset middle surface, accept that one. And now similarly we go for the down part, this part and that part, and we name as lower flange, lower flange, we'll name as lower flange, and then accept that one. And here this is also the flange, and then accept that one. And then we can cancel the procedures, and then we can see that see the the part display option, and then apply, show our I-beam is created. So apply back to that one. So we have applied the definition for the uh, cell section assignment. So we have assigned, so we can go in the part manager, and then we can see the all these three region has been assigned. And now we can go to on this lower plate, and then here we need to create the section. So there is no any section defined, and then we can now we need to select this all surface. So we can say, okay, this is lower plate, and then we select this all, and then done. And here we can select this as the plate definitions and leave everything default. So we have lower plate, and then we now cancel the procedure and dismiss that one, and go to the upper plate, and then again go to the section assignment manager, create the sections, and then we can rename this as the upper plate, upper plate, and then select all, continue, and then we are now the section plate, and leave as everything default. So, and then the definition is complete, linear material for the upper plate region has been defined, and then we can cancel. So we have defined the property, and then we can go in the assembly model, and then we can now have the view of the assembly with rendering the cell thickness, and now we should see our structure. So yes, our structures looks the way that we would like to have. Okay, so we can go in this off the render. We can off the render, and then have this default. And now our task in this is to create the spring between these 2 points. So we need to go in the SM. So let's this collapse this, and then go to the assembly, and then now there is a engineering features. Under the engineering feature we have this spring transport connections. Okay, so and we can create this one. So let's create this and then leave it as a spring there, spring there, and connection between 2 point. Yes. And now let's see the sets, if there are the sets. So there is no sets here, no sets here, but now what we can do is that we go back, and we have forgotten to assign the mass for this one, and once we create the mass, our set will be created for that one. So let's go back to the part module, and in the part module we go now to the this discrete point, and in the discrete point we need to specify the inertia for that one. So the discrete point below the lower column, so we need to create the mass, small mass for that one, because in the explicit analysis we have to give some inertia properties for the each node. So that's why we need to define some kind of point mass for this point reference point. So let's have these point mass definitions, and then we select this as the uh, that point, and we can name as default set one, and then give around 100 gram 100 gram 100 gram weight, some weight. So we have this ton unit system, so around that one, and then accept that one. So we have now the mass defined there for the discrete point below lower column. So similarly for the discrete point of the in this spring, we need to do the same procedures and then create the mass in this point, and that is 0.0001. Then we accept, and one more for the this loading point also, we need to apply the load there, and we can select this one and we apply 0.0001 as the mass. So we have this three mass defined there, and we can see in the assembly model the mass doesn't come in the assembly model, but if we go in the interaction model, then those masses, they will come there. Those masses will come there. Okay, so now we have this definitions. Now we need to go in the assembly model, and then now what we need to create is the spring. So let's go and create the spring, and under the spring we connect between 2 points, and now here we can have a set. So now this is from starting from the loading point to the in this spring. So we can select this one, and it select in the highlight, so this point is highlighted, and then continue, and the second point is the in the spring set, and then continue. So here we can see that the spring has been assigned, and let's select OK, done, and then here we can see that point 1 and point 2, and then we apply the spring stiffness value. Okay, in this case we can apply this one value, there is 32700 value as a spring stiffness, and then we can accept that one. We can accept this one, and after that we can accept this value, and then we can uh, then go back in the assembly model. So but the spring can be only visualized in these interaction models. So here we have the spring, and it is now we have modeled almost all the parts. So let's collapse this one, and now let's go to the step model. So in the step model we need to create this analysis procedure. So we will create this dynamic analysis procedures, and then some model setup, and then also we will create some output request for that one. So let's because we need to create this one in order to apply the boundary conditions and the loading in that case. So let's go to create the steps, uh, uh, and in the step, so uh, let's go in the step module, and in the step module we need to create this two step. So let's create the first step is the mechanical loading step, as it is explained in the previous tutorial. So we have this mechanical loading and the fire heating. So mechanical loading step, and the type is dynamic explicit. Then we continue, and then for the first for the 2 seconds we will have these mechanical loading steps. So the mechanical loading step is created, and then we will create another step. So that is step 2. Now we rename this as a fire heating, and then it's the same dynamic explicit procedure types, and we continue, and let's do this is for up to 8.4. So 10.4, because we have the temperature data for up to 10.4. So 8.4, then it's dismiss, and we can see in this column temperatures that we have 10.4. And now here there is a step time, so let's change that to the total time. So always in the amplitude, it is always we give in the total time in our tutorials. Okay, and here because we have defined the temperature at 0 and 2, so if we have include this mechanical loading step also, so therefore it is the temperature in the total time. If we need to give in the step time, then it should start from these points. Okay, let's leave as the total time for the time span, and then accept that one. So we have finished the step module also, and then we need to go to the interaction module. So in the interaction modules, so we will create the general contacts that is necessary for the explicit analysis. So we will have the contact definition on, and then we will create some constraint in order to connect those part with the plates. So that we will connect those plate and the colon together using a tie constraint in this one, and also have those MPC constraint in the interaction model, and then we will also create the general contacts in the interaction models. So let's go to the interaction model in the abacus, so which is the process after the step model. And so in the interaction model, now we need to first create the interaction, and here in the interaction, so we'll create the general contacts. So let's name as a general contact, and this is created in the initial step, and the type of is the interactions is that it is a general contract during the analysis procedure. So we will leave everything same, and then here we will need to just change the global property assignment as the contact. So let's name this as some interaction as it is, and then it's the type contact, then we continue, and then we have the mechanical normal contact behavior, and we leave it as a default, and then change to the interaction property over here, and then accept. So the now the contact has been defined, and then we need to have the MPC constraint for this from this point to this the plate connection point, and also similarly we need to have the definition for this point also. So first let's create a set of that edges, and then also set of the colon in age, and then it will be easy for us to connect them together. So let's go in the assembly here, assembly, and there is a set. So there are already 8 set created there. So now let's create the set here individually, and then in order to create the set, so let's hide this instance, the colon instance, so that we don't select any entities from the colon. So there is an option that hide remove selected. So we can select this one, and it will ask us to what entities to remove, and then we can select here instance, so we can remove this whole instance and then done. So this instance has been removed and then done. So here then now we can easily select these entities where we will apply this constraint, multiple constraints. So now we need to select the this up for the upper part. So let's create the set. So let's create a set and name this as MPC upper. So we can name this as a MPC upper colon. So in that upper, okay, let's name it as upper plate here. And then here we will select this point where we apply. So we will select the we will select the we will select the so we will select, so click the edges, and then with shift button we can select. Yes. So now this we can make it little big, and then it has been selected 1 2 3 4 5 6 edges, and then now we can select done, and here we can see that it has 6 edge type geometry created. In the upper side, similarly, we can also create in the lower side. So let's create that MPC for the lower side, lower plate, and then let's continue, and then let's select this point with the shift button, select the edges. Yes, and that is now selected and done. So here the lower plate also have the 6, and we can highlight that one, and also the upper plate we can highlight that one. Okay, so for the plate we have created, and then we can come back, bring that one, and now let's create a surface also for the upper one, uh, and then we can create that later, but let's create the set for the colon also. So let's remove the now let's remove so let's cancel these procedures, and now let's remove the instance, and let's remove this upper plate and the lower plate in the instance, and then done. And now we can make this tie constraint set. So let's name as a tie in the upper colon. So upper colon we can name this, and then here we can select these entities, again the 6 entities of the IB cross sections, and then we can now done. So here with the tie has been with 5 1 2 3 4 5, yes, it has been created. And similarly for the lower part also we can rotate, and then we can rotate this here and bring closer here, and then we can create a set here, and this is now tie lower colon, and then continue. We will select this and this similarly as we have selected before, and then done. So we can now see here this lower is and the upper. So lower, and then go to the default view. So this is upper and lower. So the definition is completed. Okay, so let's bring them all back together, and now let's create first this constraint, and now first constraint is this MPC constraint, and then as shown. So let's create first in the top, and then we will have the down. So now we need to give this uh, point, and it will say some eligible sets here, and this is now the loading point, and then highlight. So from this point to uh, continue that one, and then we have this we apply that to the MPC upper plate. MPC upper plate, and now it is highlighted in another color, and then we continue, and now we change this MPC is the beam type, and then we can see that we have created so that when we apply a force, that force will be distributed over these regions. And then we will also and similarly for the down part, the boundary condition will also be distributed. So let's apply for the down part also, and then create the constraint 2 is the same, and now this is in the lower column set, it is highlighted, and then continue, and now we need to go to this lower plate MPC and continue, and now it is okay. So now this is also defined, then we have the default view where we have this constraint defined, and then now we need to connect this upper plate with the column. So let's have another constraint, and now let's tie them together with the tie type, and then let's say let's have the surface, and then let's say we have the surface there, and now before that one let's remove this one. So let's remove the surface, so remove, and now here we will remove the instance. So now here, okay, then we have this surface as this master surface as for the upper plate, and then we can select that one, okay, and then blue or purple, so let's say brown or purple, and then we can choose the color, and also there is option to flip if, and then let's choose the purple on the upper side, purple, and then now choose the slab type as node, and we have already created the node set, and that is it is tie colon upper. So we have that one, and then continue, and then we will specify that only the nodes that are around 5 millimeters they will have a try constraint. So let's go back to that one. So all it will have the try constraint only in the 5 position tolerance, although we have selected these all. So let's do similar for the down part. So, and then let's remove this instance again, and then create a new try constraint 4, and then let's choose the master type as the surface. So lower plate, and then we select the surface, accept that one, and we can choose this as the purple, and then node region, and then in the set we can go in the set, and then we have this tie lower colon, continue, and then let's specify the distance 5, and then let's bring everything back. So we have this constraint, and then we can go to the interaction here, interaction property, interactions. So we have 1, 2, 3, 4. So now we can, let's suppress them, suppress. So then it is nothing shown here. Then we can now see this. Okay, let's resume this one. So it is the MPC on the upper side, that's correct. Second, resume that one, it is the MPC on the lower side. And third, let's resume that one, so it is on the upper tie constraint between the connection between the column and the plate. And now let's again go to the resume, and it has the tie constraint between the down part. So we have finished the interactions module, and now the next module is the load module, and in the load module we will apply the mechanical load, and then create the boundary conditions and define the predefined field. Here our predefined field is the temperature, so we will assign the initial temperature which for the mechanical loading, and then also we will assign the temperature due to fire. Okay, and now before going to that one, let's go to the abacus, and we know that the column is only heated around 750, so we need to create a heat zone region for that one. So for that one we need to partition the column. So let's do the partition of the column and create the heat zone area. So in the assembly model we can do the partitions. So let's go in the assembly model and then we can do the partition. So let's first create a datum plane, and after that we will partition using a datum plane. So we have this creating datum plane. Now our this principal frame from which to offset is this zx, so xz plane, and then first, so 0 0 is this point. So our lower so this is 25, so 20, so 25 above that point only is the heated and other is the fire protected. And then let's also add another one external plane, and now this is in 1775, so 25 below the upper plate. So that's the, and now we need to create a partition using those planes. So let's create a partition of the face using a datum plane, and then we can select these faces and down, and then select the datum. So here the partition has been created, and similarly for the upper part we can select these faces and then click and then down. So upper part is also selected. So what we can do now is that we can also create a set here, and that set is the heat zone set, where we apply the fire heating. So we can create a set here. So let's create a set here and then name this as the heat zone, and then continue. And now we will select this surface and then accept. So we can see in the heat zone we have that definitions completed. Okay, now we can go to the load model and then apply the loading here. So here, and also we can hide this datum. So let's hide these datums. So we can select this one hide and also select this one hide. So the datum is hide, and then let's cancel the procedures, and now we will first create the load, and the load is applied here in this first discrete point in our case. So let's go and create the load, and the load is, let's name as the mechanical loading, and then we will have the mechanical loading in this one, and then the concentration type force. And now we have this already, the load point definitions, and then continue. And now we have this 205 kilonewton, just 205 kilonewton load applied there, and then we have this we have not created the loading curve, so we need to create the loading curve, and then let's name this as the loading curve here, and then choose the total time here, and at 0 0 0, at 1 it is sorry, at 2 it is 1, and then at 10.4 it is also 1, and then we choose the loading curve and then accept. So the force is created over here, and then we can go back to that one. So in the structural analysis, here we have two steps. The first one is the step 1, which is the mechanical loading step, and the second step is the temperature loading step. So we have this heating fire heating step. So now here the loading is initially 0 at 0, and then in the first 2 seconds it is increased from 0 to maximum, so 0 to 1, and then the mechanical loading is applied around 2 seconds, and after that it is kept constant throughout the fire heating. And similarly, so this is the amplitude curve that is how the loading is applied. And similarly, in case of the temperature, so we have the temperature curve. So the temperature curve is that we have in the initial mechanical state, the temperature is initial temperature, and then after that we apply the temperature due to fire in the fire heating state. So that's how the temperature and the mechanical loading curve are used in the structural fire analysis process. Okay, so let's go to abacus. So that's the reason we have this loading curve, and then there is also the fire temperature loading curve. So, and always we use this in the total time, and this is also in the total time. So we have the define the loading, and now our next option is to define the boundary conditions. So in the boundary conditions, so we have this different boundary conditions, and also the boundary condition is applied different at different points. I mean in different loading places. So so uh, so we will now create the boundary conditions, and here the boundary conditions are applied different in mechanical step, and uh, different in fire heating step. So different boundary condition were applied in the mechanical step and heating step to avoid the axial restraint during mechanical loading steps. Okay, so first let's apply that in the boundary conditions, and then uh, we we will apply that. So let's define the first boundary conditions. So let's start from the colon lower point. So colon lower, we can name it the colon lower, and let's apply first in the initial step and the mechanical category, and it is displacement or rotation type of boundary condition. Then we will select that one. So this is applied in this lower point, discrete point. So we can select that, set that's selected, highlight it, and then continue. And we will restrain this x, y, z, and also the rotation in R2 direction. So we accept that one. So the first boundary condition is created over here, and then similarly let's create the column top. We can name as a column top, and then it's the same. And now we can choose this one, the column top, uh, and this is the discrete point where the loading is applied. So loading this discrete point, loading point, then continue, and then it is already highlighted there, and then we allow it to move in x directions, but fix this other two translation degree of freedom, and also fix the R2 rotation degree. Okay, then we accept that one, and now one more boundary condition is defined there for the initial state. So we have this lower, we need to create the boundary condition for the lower plate, left and right edge lower plate. So we can name as a left and right there, and then it is the same type, but now we don't have this set. So what we can is that we can create the set and name as lower left left and right, and then let's go on selecting them. So 1 2 3 4 and 5 6 7 8. Okay, done. And now here in the we have this it can move in so simply supported type of boundary condition. So fix u2 and u3, then accept. Okay, we have applied that one, and now let's have that one. And now in the fire, so in that's now in mechanical the load is applied, but in the fire heating steps, so additional two, so the upper plate left and right, and as well as this spring is applied. So let's apply the another boundary condition, and this is, let's name this as the spring node in point, and this is in the fire heating step. And so we have already have that spring node, so in of that one, continue, and then we fix these all. Okay, so we have fixed this all, and now next we need to apply the similar type of boundary conditions that we have applied in the lower plate. So let's create another boundary conditions, uh, and then we can name this as top plate left and right, and continue that one. So and dismiss because we didn't have the set. So let's name the set as top plate left and right. So left and right, and then we select those edges. So 1 2 3 4, and similarly 1 2 3 4. Then accept that one, and then we have this similar. So we only fix in Z and Y directions, then accept that one. So we go back, and then we can see the boundary condition manager, and here we have this. We can see that the first in the initial state, these three lower colon top and lower end are have the boundary condition, and then also we have this boundary condition at left and right edge of the lower plate, and in the fiery step we have this node where the spring in, and then also the in plate of the in edge of the upper plate. So it has, and here also we can see that initial and the mechanical loading is applied and the fire. So we have created the the steps. Now we need to create the predefined field, and the predefined field here is the temperatures, the initial temperature and the fire temperatures. So let's now first create the these nodes and the elements, and then we can see select all the nodes, and then also apply uh, the fire due to temperature in the heat zone area that we have already created. So let's go to the mesh model now. In the mesh model, so let's select the global seed type, and now let's select all, and then let's have the 20 as the minimum globe approximate size for this one. So looks okay. Then apply. Okay, and then now let's cancel, and then let's select the element type, and then let's select all, and then now explicit cell element. So by default we have this S4R, but now let's use this small whopping consider options S4R SWR4 node this element, and then okay, and then now we are done, and then let's mesh the part. select all and mesh. So we have this mesh there created, which looks like this one, and we can query the mesh statistics, and it has this total number of node 22, 23, and total number of element this is 2020. Okay, so it's okay now, we cancel, and then we need to create the node sets for the initial temperature. So we go in the set here again and then create a set, and the set is all nodes, and then the type is node, and then continue, and then we select this all node. So all nodes is selected. So now we can go to the load model, and then we can go in the predefined field managers, and then create the initial temperature field and the temperature field due to fire heating. So let's first create the initial temperature. I name this as initial temp, which is the initial temperature applied in the initial step, and that is temperature show order, and then select the type of temperatures, and then we continue that one. And now we have already created a set, so we can select that it is all nodes, and then continue, and this is 20 degree for. So here we choose direct in all nodes specifications. The initial temperature is created, and then now let's do this fire heating temperature field, fire heating fire temps, so we can name as a fire temps, and this is applied in the fire heating step, and then continue, and this is applied in the heat zone area, continue, and then we have this temp colon temperature curve and multiply with 1 for the amplitude, for the magnitude. So we have that created, the fire temperature also created, and also we need to be sure that our amplitude uh, colon temperature is in the total time. Yes, that's okay. It is in the total time. Total time. All right, and then it is also now in the total time. This one. So we have finished the load also, and also we have finished the meshing also. So now we will let's save the model now, and the model is saved, and then now we need to now we need to check the model if that everything is okay. So let's check this model one, and let's go in the job manager, and then let's create the first job. So let's name as this as a check, and then from the model one. So now let's check that everything is okay. Then let's accept this as default, and then let's have this data check, and it will ensure us that if everything is defined correctly, Abacus will check that all the keyword definitions and their relevant entities assignment, they are okay. So it has now already give us the error, so we can see what is the error here, error here, and then okay, so now here this discrete point so cannot be more than 80 character. Okay, so we need to change that one. So reference point, okay, that's also a new thing. So let's cancel this one, and now we need to change that. So the part cannot be more than one. So we can rename this part as discrete point. We can rename this as discrete point 1. Okay, so this is lower in colon. Okay, so we have renamed this now. So it means that our definitions for the constraints, it should be edited. So this is discrete point, loading point, discrete point 1, set 1. Okay, it has changed, and this is also, let's see it has changed. Okay, now we can also go in the load module, and in the load module, in this colon lower, we have this discrete point below load set. So that's reason is not available there. So discrete point below colon set 1, but now lower plate. So discrete point. Okay, so we need to go back, and then we need to go back, and here we need to also change in this property. So here we need to have this set, continue, and okay, and we have this set 1. All right, so we have that discrete point 1, and then let's go to the load module, and in the load module we need to have this lower colon, and it is discrete point below lower colon that point. So this reason is not there, and so this reason is not there in the spring and loading point. So we need to have this other definitions there. So let's change this one to this point. So edit, and then let's change that one, dismiss, and to that point, to this point. So this point, and okay, and then accept that one. So let's dismiss, and now it should work if everything goes correctly. So let's go there, and then data check that one. Yes. So in the monitor we can see that again this discrete point below lower colon is cannot be more than 80 character. Okay, so we have that still, and then we need to delete this one. So in the assembly set we have this one, so let's delete this one. So we go in the assembly model, and then so we have this one point, it cannot be deleted because it is in the instance below lower colon. Okay, discrete point below lower colon. So we have this one set 1 done, and discrete point. Okay, here we need to change this one. So we have this discrete point below lower colon 1 in the instance, so that's the reason it doesn't change, because we need to delete this one and then bring the this discrete point 1 there, and then okay, so this discrete point 1 is there, and then we need to change also the settings in other points. So we have this constraint 1 definitions, so discrete point loading 1, so this is all right. This, so there is no, so we need to, that's why we need to change that, and then we need to change that discrete point to set 1 because we have renamed that one, and then okay, so now it is defined. This is all right, third is all right, and also we have used that in the loading. So in the load definition also this colon lower in, so it changed that one, so we need to select that one to the discrete point set 1, and that's the end of the colon, and then we apply then this mesh. And I hope now this should work. So it is good to have this type of error, and this naming error I just encountered while making this video tutorials, because I also don't know that we cannot have the long character in the name. So now let's see that the packager has started and it has been completed, so which means that the check is completed. So now nothing error for the part. So now let's save it. Now we haven't saved the model, and then yes, so we have saved it, and also, and now what we can do is that we can run the model, and run the model here. So we will now try to include the imperfections, and in order to do so that I have already talked about this one, because we in this model we use these direct specifications of the temperature field assignment, and in the previous examples we have used this result from the previous thermal analysis, and also in the first tutorial we have used this in the section definition. So these three tutorial will cover different method of assigning temperature loading due to the fire after thermal analysis, and also already we have discussed about the mesh model, and here in this geometry we will consider that there is a geometrical imperfections, and the method here how the imperfection is applied is that after building the FE model or linear buckling analysis using standard abacus buckle procedure is performed using the default subspace eigensolver, and three eigen values are requested. At the end of the buckling step, the keyword node field will be written there, and to write the buckling shape in the result file, and the geometrical imperfection is applied using a keyword imperfection based on the superposition of the buckling mode shape obtained from the previous linear buckling analysis, and define associate scale factor for each mode. uh, and then we need to give the path of the result file from previous buckling analysis that is assigned in the data line where the imperfection was defined. So this is the general idea how the imperfection can be included in the geometry in the this analysis. So here also when we have this imperfection, imperfection should be included, we need to follow this type of approach, and we have followed the similar approach in the beam examples. So we can also consider in the examples. We can also submit the job without defining the imperfection. It should give somehow similar, but in some structure it doesn't, but in this structure I think it will give. But now let's see how we can define the first create these two input files, one for the buckling analysis, and then how we add these edit these input files, and then add the imperfections, and then run the explicit dynamic analysis. So we can learn this one in this tutorial, and then obtain the solution. So we have now already one model which is check completed. So I hope that there is no any mistake in this one. So what we can do is that now we can copy the model, and then we can name this as the struct, 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 structure, structural cell, and then buckle. We can name this as a structural cell buckle. So, and then also copy the model again, and then we can name this as a structural cell only. Okay, so now here we have this structural cells, everything okay, and then we need to now change the analysis type for this buckle procedures. So we go to this buckle and then go in the step module and change the step 3. So this now let's do this one is the buckle and insert after new step. So after insert this after initial step and then continue. So now it is already this dynamic type, but now what we can do is that we go there and then we we can replace this one, but it doesn't allow us to use that one. So we need to delete these two process, yes, and then let's create the buckle procedure here, and now it is under the linear permutation and the buckle, and then we continue, and here we will have this subspace, and then we will request these three eigen values, okay. And now it says that interaction cannot be used with the current procedure, so we need to dismiss this one and then go to the interactions, then this contact we need to suppress, so we have suppressed this one, and then let's go on the step model again and then define these buckling procedures under the linear perturbations and buckle, and we can name this as the buckle or buckle, and then continue, and here we request three eigenvalues and accept that one. So the buckling analysis is okay, and now we need to create the input files there. So let's create the input file. So this is from the buckle, and then we can name this as the structural cell buckle. We can name this as a structural cell buckle, and source is the model, and then continue and accept that one. So we have this structural cell buckle. So we can now go in the job monitor here. We can run this one. So let's submit the job, and here this the following part contain element not supported in abacus standard, yes. So that's true because we need to change the element type here. So that's good. Abacus very friendly user, this one. So now in the buckle procedure, so we need to go in the mesh and then change the element type. So we can select this all and then change to standard cell element. Okay. So now this should work now. Let's go to the job model and the job manager and then submit. Yes, so it has been submitted. So we need to change when we use the same model, we need to change the element type when we switch between the abacus explicit and then abacus explicit and then also the abacus standard. Yes, so we have this problem again, yes, and I think that is because we forgot to define the loading there. So good to so that it has this differential stiffness matrix is null, so and then eigen problem cannot be solved. Yes, we have forgot the loading definition there. So let's go to the load and then define the loading there. So we need to create the load and load one, and we can go to the set. So this is the loading point there, and continue, and let's have the -1 load there. Okay, so let's now go to the job and again submit the job, and now this should work, I guess, but let's see. Okay, now it is running, and then we can monitor the process here. Yes, so it has started the abacus standard, and then it has completed. So we can now go to the result here and then see the deformations. Yes, so this is the first mode that we like to have to include our geometry, and we can also animate the mode. So yes, that's how, and the second mode it goes in this way, and similarly in the third mode it goes in this way. So we have performed the this structural cell buckle ODB. So this is the result file, and we have this structural cell uh, completed. So now we need to also uh, write the input file for the structural cell. So now let's create a job again, and the job is from the cell model. So, and we name this as structural cell, and we continue that one. Structural cells is okay. So we continue that one, and now in the this is the explicit analysis, but now I just like to have the so I cancel it. So structural cell model, and then we create the input file for this one, structural cell. So, and then continue, and then okay, so we have this structural cell, and then we can do the data check on this one, and if everything is fine, then we can continue editing the input file. So now we need to go to the uh, this input file in the this directory where our working directory is there, and it is this is completed. So now we can go to this our working directory, and then here we have this check yes, and then we can sort them by the type, and we have this structural cell and the structural structural cell buckle. So we need to modify this input file. So we need to now edit the input file, and then add imperfections there, and then rerun the another analysis. Okay, so in order to do so, we have this we need to open that those files there in the notepad, and then we need to edit those. So let's go in the abacus here, and then also let's go to our this working directory, and then let's open this first buckle note in the notepad, and also let's open this cell in the notepad. Okay, and I will bring the notepad here. So we have this structural cell buckle INP and the structural cell INP. So this is our buckling analysis. So we go in the down, and before this end of the step, so we need to write this node fill u command in order to obtain the buckling mode cell in the result file. So we can control C and then control V. So we have that, and then we accept that one. So we save this one. So our new this structural cell buckle IN is created there, and then we will also have this structural cell change there, and we change this one before the step. So we can go in the step file now. We can go in the step file. So before the steps, so before the mechanical steps, so we can include the imperfection there, and then we will add this imperfection there. Control C, and then Control V, and then we need to have this result file name there. So our this result is nothing but this structural cell buckle. So structural cell buckle, but now in this input file we have not created that one. So I rename this as the input file method, and then structural cell buckle. Okay, so and then now we need to run a new job here. So let's create a job, and that is from input file, and then choose the input file. So the input file is structural cell buckle. Okay, and then now we choose this name as input in front, which meaning that it is the input from the input from the this. And then okay, so we have this input structural cell buckle. Then we can submit this job, and then it has this node u in the return. And then here, so on the structural analysis, so we have this input cell buckle that should be defined. So and that is the result file which is obtained from here, and it is completed, and we can go in the results and see in the results that okay, it has first mode shape, second mode shape, and third mode shape, but our failure mode shape is the first mode shape, and we can just include the first one. But now let's leave it as in this tutorial. So let's have this all modes together. Okay, now we have edited this structural cell INP, and now let's run this file which has these imperfections defined, and let's create a job there. And then now let's go to the job module and then create a job from the input file, and then let's give the input this structural cell here. Okay, and then now let's change the name as the input in front here, as we have changed further as we have changed for the buckling analysis. So then we continue. So okay, that is already there, yes. And here we have the wrong file, so let's delete this one, and let's delete that one, and then let's see here, this should be the structural cell, and now it is this structural cell. We can copy that one, and then let's have this input in front, which means that it is from the input file, not from the models. What we have here, these two are from the model file, model of this one. And then continue, and then let's use this parallelization. So let's use this uh, more CPUs in this case, and this we need to submit this job input structural for full analysis, and then let's submit this one now. This is from the file structural cell, and then we wait for the results, and it has been submitted, and we can see in the job monitor window that if everything goes well, then we can have the abacus explicit started. Okay, so now it is now solving. Then it will take some time, then we can view the results. Okay, so the abacus explicit, it has been started now, and then we will see the force increment, and then we need to wait for a while in order to wait for the results. So let's wait for the results. All right, so we have finished the simulations, and now we can check on the results. So let's check on the result here, and then we can go here, and then we can check the deformations in axial direction. So now this is the simulations of the structures, restrained column, and then we can go in the last one, and then we can now check the plot of that one. So we can go in the ODB output, and then choose the U1 directions, and also we can select the node here, So we can select the node, one node here, and then select that one node with the middle button, and then we can plot. So we have similar response as we have here in the in the in the in the in the post processing. So we have this type of similar response, but now here we have a temperature versus the displacements. But now here in the we have in the time, and we can do similar for the temperatures. So so here in the output request we will add some in the model. Here we in the model step, so we will add, we'll edit this output and then add the temperature also there, and then little bit with more time, then with 0.1 steps we will add the we will add this one, and then again check the new version of the solutions. All right, okay, and and let's change this one, so we can change in this one, and then run the new new analysis again. But now okay, so we can accept this one, save this one, and we have edit this, we have this added temperature, and we can also remove this stress and strain for this moment because we don't need, and also the force and also the contact. So we need the UN temperatures and those things written in the result file, and then let's dismiss this one, uh, and now here, so we can go in the job manager there, in the job manager there, and then we need to write the input file for this one. So so write input, and then before that write input, yes, okay. So it now it has written the input, and then we can go to the we can go to the we can go to this we can go to our directory, and here, and then we can edit again that one. So let's go in the notepad, and in the notepad, and then we can see that output request for this one will be changed. So we have this element output request temperature, and the history request, the temperatures has been assigned there. So the temperature has been there, and also u. So now but we have updated that one, but now it will delete this this imperfection add. Then we need to again add the imperfection there. So let's add the imperfection again there, and then also we need to change the name. So we need to also change the name there. So that's so here we have this the input of that name. So this is this input structural cell buckle. So input structural cell buckle, we can change that one name. So let's change the name here. The file name is input then is structural cell and buckle. So we can see the input structural cell and then buckle. So we have, then we will save this one. Okay, we have saved that one, and then we can run this one. So we can run this this input structural analysis cell. So we can submit this again, and then run that one. So there is already result file, but let's erase that one and submit it, and then I will come back when the results are available. Now we have finished also the another simulations where we have requested the temperature data as output, and then we can go to the results. Now we go to the result, and then we have this result, these deformations, and here we have the temperatures showing here, and also we have this deformation. So now we have only limited our output for certain variables. So let's now plot the response in the middle of this lateral displacement of the column and then axial displacement of the column. So in order to do that one, let's hide this upper part, so we can hide this one and get the displacement of this node. So let's I have hide that one, and then we can get to the create xy data. Under the create xy data, then ODV fill output, then we continue, and under the position we choose unique nodal, and we have take the temperature and the spatial displacement u1 and u2, and then we need to select the node. So now let's select this node, one node, and then also one node, some closer node from here. So let's shift and then edit selection. So two node has been selected, and then let's save this one. Okay, so we save. So there is, now we need to know what is the correct node for that one. So let's have an inquiry of the node, and what is the node. So this is 483. So 483 is the node in this point. So this is the 483 is the lateral axial displacement of the column, and this 877 is the lateral displacement of the column in the mid span. And then we can bring that part together, and then let's now plot that. So let's plot first the first the lateral displacement of the mid, so it is in like that. And for the temperature difference, we can and here is the temperature at this point. So we have these temperatures. So let's combine this plot together, and there is this create xy data, and then we can operate in xy, and then there is a command combine here, and the first is the temperature at 877, and then we have this u1 at 877. So this is u1 at 877, and save this as this we name this as lateral displacement at mid span, mid of the column, mid column. So we can name that one, and okay, here this x value cancel. So save as. Okay, x value is monotonic and interpolation is not undefined, which means that we need to choose this combine, and we choose this value at, no, not in this position, but let's change and again do. There are two combine, there should be only one combine, and we have that temperature at, sorry, so let's do it combine, combine, then we have this temperature at this 877, and then we have the displacement at 877. Save as. Okay, we have now this problem in this one, and we can also see this U2 at this plot, so we have also similar plot as it has been shown in the analysis so it is the similar uh, curve shown here. Okay, so have we have come to the end of the tutorial, uh, and this is the end of the tutorial, and thank you.